Hello everyone. So today I'm going to review all the 8 labs for EE341 lab. So the exam is going to be take place on Monday for section 1 and 3 and on Wednesday for section 2 during their class hours. I will upload the groups because I have to divide you in 2 groups. The first group will come in the first hour, second group will come in the second hour. I will upload PDF in the announcement section for each section, section 1, 2 and 3, and then you can see your timing to come to the university. So please, it's better that you arrive to the university 15 minutes before the exam. So exam will be 1 hour. So let's start the review. So this is the first lab. In this lab, we studied the basic introduction to the MATLAB. So this is the workspace. So in this lab, in this course, we were using MLX format editor, and then we were viewing our figures in the side window. So this command CLC will clear all the input and output from the command window. Then, so MATLAB, the M file is the file where we are writing our code. So already you are familiar. So, but we were using, instead of this, we were using new MATLAB live script. Okay. So then we save the file like this, press the save as, and then file is saved. Then this is all about it. So first of all, we will go through how we plot a function. For example, if we have a function f of x is equal to sine of x, then we plot it by f is first of all we have to define the interval. Okay, so defining the interval, how? First initial value, which is 0, then increment, and then final value, which is 2 pi. So increment is 0.01, increment is 0.01, and then this column will separate, and then 2 pi is the final interval. So this is initial value, this is initial value, this is increment, and then this is final value. Then we have to define the function. We have the function is f of x is equal to sine of x. So in MATLAB we will define it like this. This colon operator will prevent to print the results in the result window, okay, in the command window. So then we have to plot. So for example, we want, if we plot, write the plot command, it will plot continuous signal. If we write stem, it will plot discrete values like this. So this is the solution. So 0 pi by 100 is the increment, and 2 pi is the final value. So sine of x is my function, and then plot x. Scale is important. First you have to write the scale and then function. This will give me the plot. That's it. Then plot the function. Here we will plot the same function in discrete domain. So simply we have to write stem instead of plot. So plot that sine wave in discretized domain. So then these are the different methods to write the labels. For example, x label, this will write the x's here. Y label will give the value here, and then title will come here, and then grid means this grid will be on. So then, f of x is equal to sine of x on the interval 0 to 2 pi. So we just have to plot it. We already defined our function. So this was 0 to pi by 100 was the increment, and then 2 into pi was our scale. Then f is equal to sine of x is equal to this. So first we will define x label. X label will be come like this. So x will be 0 to 2 pi like this, and then y will be sine of x. So, and then plot this title will come here. So this will plot my function like this. So you see that if I remove the ink, so you see that here this is title, here this is y axis, and then here this is x label. Then you can plot in different colors. If you write y, so this way for here, like, so you write plot x, y, and then color. You will define color here. So if you write y, the output waveform will be yellow color. If you write black, the output waveform will be you have to write k in order to get the output waveform black. So the default color is blue. Always, if you don't write anything, if you don't just write this, it will give you blue color. Okay. So then plot the function f of x on the interval 0 to 2 pi. Here, this will give me the dotted waveform of the same sine of x function. Okay. So this is dotted version because of this, and then color is red. So plotting multiple graphs on the same single figure, so we can do that also. Just we have to define first function here, second function we have to define here, and then plot x. X is the scale, f is my first function, and then dotted, then x my scale, and then y, and then the second function. You can see the result is here. Then sinc function, this is sinc function. How we can plot the sinc function? The same thing. First we have to define the scale, then we have to define the function, then we have to plot, and then give the labels. That's it. Okay. So matrix, you can write the matrix in MATLAB by this command, A is equal to 1, 2, 3. This column, if you write this column inside the square brackets, this will give the second row. This will change the rows. Okay. So 1, 2, 3 is here, then change the row, 4, 5, 6, then change row, and then this. So if you want to write A plus B, so this will add A in B and then give you the result A plus B. So for example, we have another matrix. So we have to make the multiplication of A with B. So we have to put the dot operator in MATLAB. So this dot is very important because this will make point-to-point multiplication. For example, it will multiply this with this, multiply this with this, because 1 into 1 is equal to 4, 1, 2 into 2 is equal to 4, 4 into 3 is 12, 4 into 9 is 36. So point-to-point multiplication like this, because of this dot operator. Okay. So 7 into 6 is 42, so it's here. So 8 into 2 is 16, it's here. So dot operator will make the point-to-point multiplication. Okay. This is important. Then, for example, I have a signal which is function sine of t. I have another signal which is sine of 10t. First of all, I will define my scale. Let's say scale s is equals to 0 to some increment, and then here, then final value 2 or like 10, whatever. So sine of t, my first step is f is equal to sine of, for example, my t is, so t, then sine of 10 into t, my second function, for example, I say it y, then multiply these two. So for example, r is the result is equal to y into f with dot, then, or this is x of t, it's written here. So x of t is multiplication of these two functions, and then I will add. So now RT is equals to xt plus e raised to the power exponential of 0.01 into t. So this is my writing of this block diagram. So you can see here that first I define my scale. As this is sinusoidal, so for this we have to always define the increment in pi. Okay. Then first function by sine of t, this one, second function sine of tan t, and then xt, this is the multiplication of a and b. Then rt is xt plus exponential function. Then plot, this will give me the first plot, this will give me the second plot. Okay, so here, that's it. That's all about lab number 1. So now lab number 2. Here in this lab, we learn to implement some basic communication signals in MATLAB. So such as the signals are direct, which is delta of t, delta function, which is one impulse at 0. Then unit step, which is starting from 0 going to the infinity. Then rectangular function, so it can have some interval here, some interval here, and then sine wave. Sine wave, we already know how to plot it. Next, so zeros, this command will give me zeros, a vector having zeros. So this number will define how many zeros. So this will give me a vector of zeros. 1 will give me vector of zeros, and then this will give me the number of elements in that row. Then, for example, if I write 10 into 1s of 1, 4, it will multiply this amplitude 1 with 10. So I will get all 10s. So these are some basic things to know. Then this is my delta function. So how I write it in MATLAB. So my first step is to define the scale. So this scale is going from -5 to 5. So if there is no increment, then MATLAB takes increment of 1 by default. Here you can see that the increment between these two intervals is 1. Then defining the delta function, how we define the delta function? We say that at n is equals to 0, at n is equals to 0, the amplitude is equals to 1. The amplitude is equals to 1 here. So, and then rest it is 0. So by this command, it will give me one amplitude only at the value which is equals to 0. Then stem and d means give me an impulse at the value 0. Then this is title here. Then this is x label. Then this is y label. That's it. Then unit step, which is starting from 0, it has amplitude of 1, and then it goes to positive infinity. Okay, and then for example, if I just want to draw a unit step function from 0 to 1, then I have to write u of t, because you see that u of t is from 0 to infinity, and u of t minus 1 will be starting from 1. So if you minus this function from this, if you minus this function from this, it will give you, this will be cancelled out with this one, and then I will only get amplitude from 0 to 1. Only I will get this part, because this will cancel, go to 0. This minus this, 1 minus 1 is equal to 0. It will be 0, and then it will be only 1 at this, because here it is 1, here it is 0, 1 minus 0 is 1. So it will give me this window. Okay. Then how to plot unit step function? The first step is defining the interval, which is from -5 to 5, and then here, as I'm going to plot a continuous function, so I have to give this increment. Okay, in the stem or discrete, I don't have to give the increment; it will by default take 1. But in the continuous, I have to give the interval. Okay, the shorter, the less is the interval, the more smooth is the waveform. Okay, now how I defined here, so u is equals to 0 for all the values which are less than 0. Okay, so it is 0 for all the values less than 0, it is equals to 0. So it's 0 here. Then it is 1 for all the values greater than 0. Okay, so it is t is equals to 1 for all the values greater than 0, it is equals to 1, and then here this is 1. Okay, this is the procedure to define any this kind of function. So then plot, and then these are the title, y-axis and x-axis. Then the same thing, but we will plot it in discrete domain. So stem and u. Then this is a rectangular function. So this is here we just have to define that. So what we can write here. So t is equal to 0 is equals to 0 for all the values. Just write here. So here t is for all the values less than 3. So t for less than -3, it is equals to 0. This command, and then here also it's 0. So we have to write and t greater than 3. So it is 0 for all the values less than -3 and greater than -3. And then it is 1 for all the values greater than or equal to -3 and less than or equal to 3. So it's here. So then plot t rect. Rect is this function which I defined, and then title x label and y label. Okay. Then the same. So now the same thing in discrete, just changing this now. Plot to stem. Okay. So now the two parameters are used to define a periodic sine wave, this amplitude and then its frequency omega naught, which is equals to 2 pi f. So if you want to define a sine function, you need two things. One, its amplitude, and one, its frequency. Okay. For example, I want to define a sine wave. So sine wave starts from 0. So first of all, I will define the interval, then I will define the frequency. Okay. So and then I will define amplitude. Now the two things are complete. Now I have to write omega naught, which is equal to 2 pi into f. Just write the same, this function here, a into sine of omega naught of t, and then plot. So this is it. Now, what is sampling frequency? Sampling frequency is the number of cycles per second. Okay. So this is the sampling frequency. So this gives the value of the function at sample n as y of n is equal to a into sine of omega naught divided, because omega naught is equal to 2 pi f divided by f naught. This is the sampling frequency. This is the frequency of my signal. Okay. So we have to plot a discretized, whenever we have to plot a discretized version of a sine wave, we have to define its sampling frequency. So which is equals to 500, the fundamental frequency, the signal frequency f naught is equals to 10 hertz, and then the amplitude is equals to 2, and then number of samples is 60. Okay. So first of all, I will define total number of samples. Okay. Then this signal will go from n0 to n minus 1, means it will go from 0 to 59. Then f naught is equals to 10. This is the fundamental frequency. It's given in the question. Then fs, and simply we have to write this equation, this same equation here, and then after that we just plot. Okay. Then this will give me the, for here, if you can see that. So this will give me the discretized sine wave, and then this is for the frequency 10 hertz, and then when the sampling frequency is equal to 100. So what you have to do is, first when f is equal to 500 and f naught is equal to fundamental frequency is 10, the waveform is this one. Then you will increase, you will decrease the sampling frequency, and fundamental frequency will be the same. Only you have to write this here 100 and then plot. You will get this waveform. Okay. So you will get two waveforms for two different sampling frequencies. Okay. Number one is this, number second is this. You have to just change one number here. That's it about the second lab. Now go to the third one. This in this lab we are going to make a Fourier transform and inverse Fourier transform using MATLAB. Okay. So x of t, if it will go in the, if I want x of t in frequency domain, t is time domain, omega is equal to frequency, so 2 pi f. So this is frequency domain. In frequency, I have to take Fourier transform to transfer it to frequency domain. And x of omega, this is a frequency domain, and then if I want it back in the time domain, I have to take the Fourier transform. So I have to take inverse Fourier transform. So x of t inverse Fourier transform of frequency domain signal will give me the time domain signal. Okay. So only I will use Fourier command for determining the Fourier transform, and I will use I Fourier, inverse Fourier, to determine the inverse Fourier transform. So how I will do it? I have to define the symbols. S, Y, and S will give me the symbolic representation of the numbers. For example, if I define A, B symbols, then at my output, I will get the output in terms of the symbols, not numbers, not 1, 2, 3. Okay, so that's why I have to define symbolic variables using this command syms. So if I want to take Fourier transform of f is equals to a cosine of omega naught of t, so what I have to define is this symbol, and this symbol. Okay, so I will write syms a omega naught. So here I wrote it. Let me. So a t, and then omega naught. Then I will write my function and then just Fourier f with omega naught. If I define omega naught, so f with omega naught will give me its Fourier transform, which is a into pi delta of t minus omega plus delta of t plus omega. Okay. So now this is a rectangular function. For the rectangular function, I have to define its first value, and then I have to define its last value, and then t. Okay, so this will give me the Fourier transform of this rectangular function, and then rectangular pulse will give me this rectangular function. Okay, then heavy side is for defining unit step function. Then here we will define a triangular function. So triangular pulse will give me the triangular function. So this 0 is the first number, 5 is the second, and then this 5 is the amplitude, and then t is my scale. So just writing f omega will give me the Fourier transform of this triangular function. So for example, when I will define inverse Fourier, then here I have to write f with t. In case of in case of determining the Fourier transform, I will write here omega. Then this is the function. So e raised to 1 minus t square minus x square. I will define it here, and then all the variables I will define here: t, x, and omega. Always it will be there because I am going from the time domain to the frequency domain. I have to define it. So e raised to 1 minus t square minus x square. This I define, and then with this command I will get this answer. Okay. Then now I will determine the inverse Fourier transform. So t is the continuous domain, omega is the frequency domain, and n is discrete. So first of all, I will define symbolic variables omega, and then t or t naught, because we are going to we are going from frequency domain back to the time domain. So I will define my function, and here I Fourier x1 with t, because now we are going back to the time domain, so we have to write t. You remember that with the Fourier we were using f with omega. Here we will always use my function with t. Okay, then this same I will define my function. First I will define omega, and then t, and then inverse Fourier transform. Okay, then now this is the command ft will give me the discrete Fourier transform of any function, any time domain function, where n is the number of points. So here I have to define the number of points for my Fourier discrete Fourier transform. So what I will do is FFT of xn, n is the number of points. So how many number of points I want in my output, and will define that. And then here I will normalize it with k. This will return n point DFT normalized over k. Then FFT shift will rearrange the Fourier transform by shifting to the zero frequency component to the center. Okay, so these all we need in Fourier transform when we use FFT. So this I told you that this will give me the absolute, because this is a complex number. If I want to get absolute value, so abs of this C will give me the absolute value. So for example, let's m is equal to sine of omega naught of t, where f naught, like I know that 2 pi f naught is equals to omega naught. So f naught is equals to fundamental frequency is 5 hertz, and then interval is 0 to 3. Let the increment be 0.01. Okay, first of all I will define the scale. Now I have to find the sampling frequency. So the sampling frequency I will get just by dividing with the increment. 0.01 fs will be 1 divided by this, will give me the sampling frequency. Then find the Fourier transform of m. I will define my signal, and then I will find FFT of my signal. So the steps are, first of all, I will define my time scale. So it will start from 0 and at 3. F naught is given fundamental frequency. So my signal m is equals to 2 pi sine of omega naught of t. And then my length of signal and total number of points will be up till length of m. So number of points will be same as the length of this my signal. Then sampling frequency I will define, this is part A. F is equal to 1 divided by increment. Okay. So then line space minus Fs. So what does line space do is, for example, it gives you different, for example, if you have a vector 1, 2, 3 up to 4 and 5, you see that there is an increment of 1. Okay, if I write here for line space 0 and then 5, okay, and then I don't write this, then it will give me samples from 0 to 5 with an increment 0 to 5. It will give me 100 samples between 0 and 5. But if I define here number of samples, then what here this n will be equal to, n is equal to x2 minus x1 divided by n minus 1. Means, so this is x2, this is x1 divided by n minus 1. So this will give me the increment of these points. So what I want. So between these two, it will give me the increment. So this is important. This is same like the colon operator you use here for increment, but this will give you more control on your signal points. Okay. So then m1 is equal to FFT of m, my signal, and total number of points divided by the total number of points. FFT shift will shift the zero frequency component across 0. Then absolute, then Fs will give me the absolute value of all these frequency which I get. So I can just write these 3 commands, or I can just write absolute of FFT shift of FFT of mn divided by n. This is the same. So then plotting. So this will give me the time domain signal. This will give me the frequency domain signal. So you can see that here I got the frequency domain signal of my sine of omega naught of t, which was my original signal. Here, when you have this signal, if I ask you that how much is the frequency of this signal, then what you will do is you will count the peaks 2, 3, 4, 5, and here almost 5.5. So 5.5 Okay, so so you know that 1 divided by the total is 3. So 1 divided by this, so it will be 5.5 samples per second. Okay, so you see this, my frequency was 5 hertz, and then here I can get 5 peaks, 1 2 3 4, almost 5.5 peaks. So this is half, so almost 5.5 or 5 is my frequency. Okay, so then here you can see that this, if I ask you to find the frequency of this signal, so you can exactly map it in the middle point. So this middle point 5 is my frequency. Okay, so this you can verify with your question also, that your frequency of the signal is 5 hertz, and then these waveforms also give you the same frequency. Okay, so then that's it. So for lab number 4, here in this lab we have amplitude modulation. So what is modulation? So modulation is transmitting your signal through a channel and then receiving it. Okay, this is transmission and then this is channel. So for if I just transmit my original signal directly, I will lose all my signals. So what in modulation, what we do is we multiply it with carrier. Okay, and then transmit. So in double sideband suppressed carrier, my carrier, at when I will get my received signal, the carrier component will not be there. Okay, so here and then double sideband suppressed carrier is an example of amplitude modulation. For example, this is your signal, message signal, this is your carrier. When you modulate it, you will see that there is a variation in the amplitude. It means this is a type of amplitude modulation. So what we have our message signal, we have carrier, and then we have our modulated signal. Okay, so f is equal to 1 by t, you already know. Then omega is equal to 2 pi f. So my when I am doing the modulation, my scale will be 0 to 1 by fs. So this will give me increment, because you know that when I find fs, to find fs, I divide it with the increment. Okay, so or I can write the increment 0.01 is equal to 1 divided by fs. So this is just an increment. Okay, then 4 is the number of cycles, and then fm is the frequency of my message signal. Okay, so then y is equals to 1 up to 9. So this is an example to tell you what does length space mean. So length is equals to length of y. This will give me the total length of y, which is equals to 9, because there are 9 samples. So length space 9, 81 and 1. What it will do, this is my x1, this is my x2, and then this is L. L is equals to 9. So what it will do is it will give me 9 samples starting from 9 up to 81, and then it will make an increment of 9 between these two. Okay, total it will give me 9 samples. Okay, 1 2 3 4 5 6 7 8 9. Okay, so this is almost similar with the increment operator, but it gives more control on your output. So this I already explained you. This is the way to define any periodic signal. So then I need amplitude, I need frequency. Two things to define any signal, periodic signal. So FFT, I explained in the previous class also. FFT of X will give me the discrete Fourier transform. If I have a time domain signal and I want to transform it to the discrete time signal, so I will do FFT of that signal. Then I have to normalize it with the number total length. Then FFT shift will shift across the 0. shift zero frequency component exactly in the central, and this is absolute value. So this we already studied that we can combine all three commands, absolute, FFT shift, and FFT of this signal. Then, so here you can see that the carrier is here, but in double sideband suppressed carrier, this carrier will be removed. So what you have is, you have your message signal, you multiply it with carrier, you have X of t. You will pass it through the channel. If the channel is like distortion free, it's ideal channel, then you will get Y of t, which will be equal to X of t. Then at the receiving end, you will again multiply it with the carrier, and then you will pass it through the low pass filter to get your estimated message signal. So this is the modulation technique. So here in this lab number 4, we will only do this step, and then we will just plot time domain and frequency domain signal, X of t, M of t, and carrier. Okay, so only this we will do. So M of t, X of t is equals to this carrier multiplied by M of t. So here, then here is, so what again we will multiply at this point, we will again multiply this Y of t, which is equal to M of t into AC cosine of 2 pi f ct. We will multiply it again with AC cosine of 2 pi f ct. So by trigonometric identity, we will, so when we have cosine of alpha, cosine of beta, I can write it 1 plus cosine of alpha. So this is the trigonometric identity, and then the constant terms will come here, and 1 plus cosine divided by 2. So this cosine of this first and cosine of this second will give me 1 plus cosine of alpha beta divided by 2. So this is the trigonometric identity. So we will get our V of t, this signal here, exactly like this. And then after passing through the low pass filter, this frequency component will be removed, and then we will only get this signal, which is here. So in this lab, only we will do this part. Only we will message, we will plot carrier, and then we will plot modulated signal. So we have a question that use MATLAB to generate double sideband suppressed carrier, knowing the carrier frequency is 154 kilohertz. So sampling frequency is 100 times FC, it's given in the question. Then frequency of the message is 10% of the carrier frequency. So FM is equals to FC divided by 10. Okay, then or FC multiplied by 0.1. So then this is multiply. Then show the message signal, carrier signal, and transmitted signal in time domain. First we will plot time domain. Second we will plot frequency domain. So first of all, I will define my carrier frequency. Then I will define FM, which is equal to FC divided by 10, as it is given in the question, as I told you here also. So then I will define my time scale, which is T, then this increment, and then number of cycles divided by the frequency of the message signal. Then amplitude is equal to 10, it's given in the question. So I define my message signal, then I define my carrier signal, and then I multiply, because I know that this M is multiplied with carrier, and X of t is equal to M into C. So I did the same thing here. Okay, then simply plotting. So this will give me, this is T, so this will give me time domain signals, waveforms for carrier, message, and the modulated signal, transmitted signal. Then here for the frequency domain plotting, I will first define the number of samples, n, total number of samples, n is equal to up to length of my final signal, X of t. And then length space will give me the number of points, and then this will it will start from minus to minus fs by 2 2 plus fs by 2, and then this n is the increment. Okay, so how many? So n, I told you this will be x2 minus, for example, this is x2, this is x1 divided by n minus 1. So this will give me the increment between this. Okay, between my fs by 2 and minus fs by 2 and fs by 2. Then absolute value of FFT shift of FFT of M. This is my message signal. This is my carrier signal. This is my transmitted signal. So it will give me the first. It will give me the Fourier transform. Then it will shift it across 0, and then it will give me the absolute value. Okay. So you can, and then here it is only plotting. So what does this axis is doing? So this axis will give me, so the axis will be from minus 2 fc to 2 fc. So you can see, if you see the figure here, so it will give me from minus to plus, and then this is my amplitude, and then this is the starting number. Okay, so this will define my axis. Okay, then this will give me the carrier fc. Then this will give me the frequency domain representation of my message signal. This will give me the frequency domain analysis of my transmitted signal. Okay, so at the end you can see that this is my carrier signal. So if you see up till here, if I ask you to find the frequency of this signal, so you can count the peaks: 1 2 3 4 5 6 7 8 9 10 11 12 13 14, and then this is half 15, and this is full up till here 15, and then this is 15.5 because half is here, so 15.5, and then divided by 10 raised to the minus 4 will give me 15.5 into 10 raised to the minus 4, which will be equal to 155 into 10 raised to the power 3, means 155 kilohertz. So this is same here, 154 kilohertz. Okay, so this is the method to tell the frequency. Then, so one thing, so then this is my message signal. I can find the frequency for this also. Up till here I will, so it's 1.5 peak. This is full peak, this is half peak, so 1.5 divided by 10 to the minus 4 is equal to 15,000 hertz. So this is 15,000 hertz. So this is my transmitted signal. Okay. So then in the frequency domain, this is my carrier signal. So you can see that the frequency, if I ask you what is the frequency of this signal, then you will see it that it is between minus 1 and 2 is 1.5 or 1.5. So 1.5 multiplied by 10 raised to the power 5 will give you 15 kilohertz. So 15 kilohertz is the frequency of this carrier signal. So then 10 raised to the power 5, so it will be 150,000. 150, yes, this because this is 10 raised to the power 5, so 2 points will be come here, 150 into 10 raised to the power 3, so this is 150 kilohertz. So here you can see this is 1.5, so 1.5 into 10 raised to the power 4 will give me 15 kilohertz. Okay, and then in the modulated, so in the middle is the frequency. You can see that carrier frequency is suppressed. Okay, so this is it about lab number 4. So then lab number 5. This is related to the double sideband suppressed transmitted carrier. Before, the carrier was suppressed, but now the carrier will be there between two bands. Okay, so this is also the amplitude modulation. What we have is we have transmitter, we pass it through the channel, adding noise at the receiver. We do some process of manipulation with carrier, and then passing through the low pass filter, we get our estimated signal. So transmitter, at the transmitter we generate message, we modulate message. How we modulate message? We multiply with message with the carrier, and then this is amplitude modulation. Okay, then okay, so here in this case we will add a DC offset. Okay, because at the output we have, for example, our waveform will be like this. We will have envelope. So for that we need to give the DC offset, so our wave will be shifted upward so that it will be easy for us to extract the full envelope of the signal. Okay, so what we do is we will add DC offset to our message signal, then we will multiply it with the carrier, then we will pass it through the channel at the output. What we will do is we will multiply it with the carrier, and then we will pass it through the filter, and then we will get our estimated signal. So first message signal, then add DC offset, multiply with the carrier, pass through the channel, then receive signal, multiply with the carrier, pass it through the narrow pass band pass filter, and then you will get estimated signal. You need to remember this block diagram. Okay. Then first of all, I have my message signal, then this is DC offset. This will be added in the message signal as according to this block diagram. Then carrier is equals to same AC cosine of 2 pi FCT. Then transmitted signal will be this plus this A naught plus M of T multiplied by C of T as per this block diagram. Please remember the block diagrams because they are important. Then at the receiver, what I have is X of T is A naught plus M of T. So this was my signal here into C of T. So filter output will be, filter input will be A naught plus M of T. This signal A naught plus M of T into the carrier signal, and then again multiply with the carrier signal here. So this is my signal which I received here. Here, this is the signal. Then this signal will pass through the narrow pass band pass filter, and then I will get my estimated signal, this one, because this frequency component will be removed by the filter. Okay, if you understand the block diagram, it's easy to write these steps. So then in the narrow pass band filter, so it will rectify. So first of all, this will be the rectifier, so it will give you this envelope. You see that this will be removed. So that's why in the beginning we were adding a DC offset to shift our full signal up, so that when it will pass through the rectifier, this part will not be lost. Okay, so for this we are adding a DC offset in the beginning. Okay, so my filter design is the filter which I will design for this lab is Butterworth filter. So this is the order of the filter, and then this is the cutoff frequency FC. And then I will pass my signal. This AB is my are the numerator and denominator of the filter, which are here. And then this Y is my signal. Okay. Then this is the time scale. You are already familiar. This is 0. This is increment. Then this is number of cycles per the message frequency. So this will be the same everywhere. So then FFT, same thing, xn divided by n, and n is equals to length of the signal. In this case, my received signal. Okay. Then FFT shift. This is for the frequency domain analysis. So you know that FFT shift will shift the zero frequency component exactly in the center of the array. So then modulation index, this will define that to how much extent the wave will be modulated. It's given by MP divided by A naught. So this is the maximum frequency of the message signal divided by the amplitude of the message signal, amplitude of the carrier. Okay, so we will see that when the MP is, this is the maximum peak of the signal, this is the negative peak of the signal, this is my message signal. When A plus, this is the DC offset, A plus M of t is greater than 0, then the situation is this will be slightly up than 0 axis. So if this is not greater than 0, so you see part of this is going in the negative domain, and then you see that in the here, so A plus M of t is enveloped, so there is a negative part here. So when I will take the modulus, so this negative part will be removed, which I don't want. That's why it should always be greater than 0. The DC offset should be greater than 0. So then, so this is modulation index cases when it is 50. So that you know that modulation index should be from 0 to 1, between 0 and 1. Okay, so if this is perfect modulation, this modulation is also acceptable, this is fine, but this is over modulation when mu is greater than 1. So this is over modulation. Here you see this part is lost. So this is perfect modulation when mu is equals to 1. So here this is perfect modulation when mu is less than 1. So this is acceptable, but this over modulation is not acceptable. Okay, then we have our example. So we have to simulate the given system, this system. The message signal in the time domain, first of all, we have to plot in time domain and frequency domain, and number of cycles will be 5. The carrier signal we will first we will define carrier signal, then we will plot it in time domain and then in frequency domain, then transmitted signal, plot in frequency domain and time domain, and then estimated signal output both in frequency and time domain. First of all, we will generate message signal, we will generate carrier signal, we will add DC offset in the signal, then we will pass it through the channel, and then we will multiply with the received signal, we will multiply with carrier, then we will pass it through the narrow pass band filter. So we will see that we have to check for different DC offsets. Okay, so what will be the effect of this DC offsets? So here the signal is FM is equals to 20, amplitude AM is equals to 1, and FC is equals to 500, and then amplitude is equals to 1, sampling frequency FS is equals to 8000. Okay, cutoff frequency is, this is needed for the filter, Butterworth filter. First order filter is 1, and then cutoff frequency is 0.01. So you know that you have to define A, B is equal to this filter. Okay, for this you need this last line. Okay, then defining the carrier frequency, then defining the message frequency, defining the sampling frequency, defining the time, number of cycles is given in the question, then n is equal to length of t, this is for the frequency domain, and then this also is for frequency domain plotting. So then first you will define carrier signal, then you will define message signal, then you will add a DC offset here according to this plot diagram. Then you will add, you will get modulation, you will multiply A naught plus the message, multiply with the carrier. Here this is x of t, which is the modulated signal. So this is all done up till here for the time domain. In the frequency domain, you will define your carrier. So this familiar command. So, but here the difference is here, this is C for carrier, M for message, and XT modulated signal. Then just plotting, and then here this is the plotting for the frequency domain. Okay. Now at the receiver, so this was all done until here for the transmitter. Now this at the receiver, you get x of t, you get your received signal here x of t. So x of t, again you will multiply it with the carrier. Here I did this step is here. Then you will pass it through the filter, you will design your filter, you will pass your this signal from the filter, and then you will get your estimated signal here. Here you will plot your original message signal, and then here you will plot your estimated signal. That's it. So this is the carrier signal, this is the message signal, and then this is the transmitted signal for the when your amplitude is equals to 1. Here I define mu is equals to AM divided by A naught. So for A equals to 1 is my this modulation. So this is the frequency domain, and here you can see that carrier is there in the transmitted signal. The carrier is not suppressed. So carrier is exactly at 500 Hertz. Okay, because the frequency of carrier was 500. Frequency of the message signal is 20 Hertz. Frequency of carrier is 50 Hertz. So you need to know that how you can define, how you can tell me that what is the frequency of the signal by only looking at the diagrams. Okay, you should know it. Then this is my original message signal, this is my estimated signal. Okay, so then when you will change this value to 2, then you will get this, and then here you can see that this is over modulation. I told you whenever this mu should be between 0 and 1, when it's greater than 1, so this is bad, which we don't want. Okay, then this is the frequency domain analysis for mu value equals to 2. Then here when it is less than 1, so this is good. Okay, so this is my original signal, this is my estimated signal. Okay, this is all about lab number 5. So we will move to lab number 6 now. So in lab number 6 we did frequency modulation. In lab number 4 and 5 we were doing amplitude modulation, but here this is frequency modulation. It means before what we were having the difference in the amplitude like this, but here we will have the difference in frequency like this. My modulated wave will be like this, difference in frequency. Okay, amplitude will remain the same. Here amplitude was varying. Okay, so this is frequency modulation. We have transmitter channel, pass it through the when we will pass it through the channel, a noise will be added at the receiver, we will get our signal, and then we will pass it through the low pass filter and we get estimated signal. Same steps. So but this is frequency modulation. You see here you have the original signal, this is the carrier, this is the message, and then when you did the modulation, here you can see there is a shift in frequency, change in frequency. At some places frequency is small, low. At some places frequency is high. So what you have is here phase shift. Frequency shift is also the phase shift. So in your carrier you will have a phase shift of this phi. So if you consider omega c of t plus phi equals to theta, which is equal to omega c t plus phi. So, and then you can write this theta equals to 2 pi f ct, because omega c is equals to 2 pi f ct, plus this phi is equals to 2 pi kf, where kf is the constant, into integral of 0 to t m of t. So this phi is equals to 2 pi kf into integral of 0 to t m of t dt. Okay, so what you have is you have your modulating signal, you will pass it through the integrator, and then here you will pass it through the 2 pi FC, and then this is your frequency modulated wave. So modulated signal will be AC cosine of 2 pi FCT plus this integrator and then message signal. Okay, so this is frequency modulation mathematical equation. Okay, so KF is the frequency sensitivity. Okay, then in practical analysis, when we want to make the frequency changes or frequency modulation, we pass it through the voltage controlled oscillator. Okay, so M of t passed through the voltage controlled oscillator. Xc of t will give me the change in the frequency. Okay, so this is the frequency modulation mathematical equation, and then this is narrow band frequency modulation equation. So what you see here, you have your this is your first waveform minus the shifted version here. So this is this one, and then here this is shifted negative 90 degree. So cosine will shift with a phase shift of 90 will give me sine, and then here this is integrator. So this is multiplied with the integrator here, and then it is multiplied with 2 pi kf here. So here this is the sum of this signal AC cosine of t minus this signal. This whole signal is this one. Okay, so this is the narrow band frequency modulation block diagram. Okay, so these are all the mathematics. So for example, you have your message signal AC cosine of omega c plus fm of t. So phi, I already told you, phi is equals to this. Phi is equals to 2 pi kfm into integral of minus infinity to t mi of t. Then when you solve it, okay, then you will get phi m is equals to beta into fm into sine of t, where beta is equals to change del f divided by fi. Okay, so this is equal to, so this beta is here also. So beta is the change in the frequency, carrier frequency divided by the fi. Okay, so then this is my modulated message signal. Okay, so previously what we were doing in amplitude modulation, simply we were multiplying our message with the carrier, but here we have to do the phase shift, and after doing the modulation we get our final signal, which is this one. Okay, so when modulation index mu is less than 1, then that is narrow band frequency modulation, and when it is greater than 1, that is wide band frequency modulation. Okay, so what we have is, at the transmitter we have k into fm, which I defined, which I told you here, that this phi is equals to 2 pi kfm into integral. So we have kfm, then for this beta fm, which is equal to delta f over fi, we have to define delta f, which is equal to kf into am, and then beta f is equal to delta f divided by f. So we have to define this. So then message is this, carrier is this, and then modulated message signal is this equation. Wrote it here. Okay, then the same thing, defining the scale, and then at the output what we have to do is, we don't have to follow that procedure of multiplying with the carrier and passing through the low pass filter. Only we have to use this command. This will do all the things of low pass filtering, and multiplying with carrier will be done here. So here you have to define, here you will write your received signal, here the carrier frequency, sampling frequency, and then fm is the demodulation method. So it's frequency modulation method, so fm, and then kfm is my frequency sensitivity, or it is also known as voltage to frequency gain ratio. Then you will get your estimated signal after passing through this. Okay, so you using the MATLAB simulate the following: the frequency deviation. Frequency deviation, you know that, which is equals to delta F. Modulation index mu. Message signal is 5 cycle. Carrier is in time domain, and transmitted signal. Then you have to because here in this case the noise effect is neglected, so you don't have to add the noise. So these are the data for the message carrier. So 35 hertz is the carrier message signal frequency, 500 hertz is the carrier frequency, sampling frequency is 10 kilohertz, and then KFM is 350, which is the frequency sensitivity or voltage to gain frequency gain ratio. So defining everything here, then defining carrier, defining the message, and then defining this equation, which I told you is this equation, this one. Okay. We don't have to multiply with the carrier as we were doing in the amplitude modulation. Here we have to write this equation. Then carrier, message, and transmitted signal. So here you will see that this is your carrier signal, this is your message signal, and then here this is the frequency modulation. When beta is equals to 10, so the output is this, and then after passing through the demodulator, I get my estimated signal here. That's it about lab number 6. So lab number 7 is related to the quadrature amplitude modulation. So I think this is very interesting lab. So here we have two carriers, carrier 1 and carrier 2 is 190-degree shifted. Okay. So quadrature amplitude modulation, we have both. We get amplitude modulation and as well as we have the phase modulation, which is similar to the frequency modulation. So we will have both in this quadrature amplitude modulation. Okay. So what we have is, we have our first carrier, we have our second carrier, which is 90-degree shifted. So we will start from here. So we will have our first message multiply with the carrier. We will have our second message multiply with the second carrier. Then we will add them and then we will transmit them. Okay. So first message multiply by carrier, message 2 multiply with the carrier, and then add them here. At the receiver, you will what you will do is, for example, here we will have noise also, because this is quadrature amplitude modulation is prone to noise. So we will pass it through, we will add AWGN, additive white Gaussian noise here. Then I will get y of t. Y of t, we will multiply it with the carrier, and then with the second carrier we will pass it through the low pass filter, and then we will get estimated signal. Okay. So remember the block diagrams, because if you know the block diagram, it's easy for you to write the signal. So then same thing, transmitter channel, we will add noise here, then at the receiver, and then we will do low pass filtering and multiply with the carrier, we get estimated signal. Okay. First of all, we will write the transmitted signal. So, okay, one thing about the adding noise. So we will add noise by AWGN. This is the command. So data mod is your signal. Then this is signal to noise ratio, means how much extent is noise and how much extent is your signal. Okay. If it is 20, then it means 20% noise is added. Okay. Then measured, this will give me the power of the signal before adding the noise. Okay. So this will give the signal power before adding the noise. Okay. Then here we already now after adding the noise, we are done up till this part. Now at the receiver, what we have to do is multiplying with the carrier, passing through the low pass filter and getting the estimated signal. Okay. Same thing, multiplying with the carrier, getting passing through the low pass filter, getting the estimated signal. Okay. So we have this question. So use MATLAB to generate quadrature amplitude modulation system to send two messages through the channel. So then use wide Gaussian noise added to the transmitted signal through the channel. Steps are, first of all, generate message signal, generate carrier signal, and then write transmitted signal. At the channel, add white Gaussian noise with a signal to noise ratio of 20, and then estimated message signal after demodulating. Okay, so this is the data. So this is for the sampling frequency fs, which is 8 kilohertz. Frequency of first message is 10 hertz, amplitude 1, frequency of second message is 50, amplitude is 4, and then frequency of second message is 200 and amplitude is 1. Then for the filter, Butterworth filter, my filter is low pass filter. It's first order. So you remember, so you have to write butter of 1 and then 10 microhertz. 10 into 10 raised to the power minus 6. 10 e raised to the power. So you have to write 10 e and then equals to a b. So let's see here. This is my given data. This is my first message. This is my second message, first carrier. Second carrier is the shifted version, and then here adding both. Then at the channel adding white Gaussian noise. Then this is my received signal. So I multiply it with the carrier, first carrier, multiply with the second carrier passing through the low pass filter. And you see, so it was 10 microhertz. So I can write it 1 into 10 to the minus 5. Okay, so it's done here. Then you can write 10 e minus 6, or you can write 1 e raised to the minus 5. It's the same thing. Then passing the first received signal through the low pass filter, passing the second received signal through the low pass filter, and then here plotting. Okay. So you see, this is your message, this is your message 2, this is your carrier, this is second carrier, this is your transmitted signal, and then this is your received signal, and then here is your estimate signal 1, there this is your estimate signal 2. Okay, so that's it about lab number 7. So let's go to lab number 8. So in lab number 8, we did the sampling. So we studied about sampling theorem. So sampling is actually discretization of a time domain signal. So like this. So getting the discrete version of a continuous signal is known as sampling. And then when I want to return back from this sampled version to the continuous domain signal, I need to fulfill a criteria, which is fs should be greater than 2 into maximum frequency of the message. If this condition is satisfied, I will get my reconstruction of the signal correct. But if this condition is not satisfied, then my sum of the information will be lost. Okay, I will not get the actual signal back. Okay, so for the sampling, what you have to do is, for example, you have an analog signal, you will multiply it with impulse train. Impulse train is like this, then you will get here this sample signal. Okay, so x of t is this signal, impulse train del of t is this, and then multiplying these two will give me sample waveform. So this is the same thing here. Your analog signal multiply with the impulse train, and then you get your sample signal in time domain. Here impulse Fourier transform of this is here impulse, then this is impulse train in Fourier domain. Okay, this is one impulse, this is impulse train. So if your that condition fs should be greater than or equal to 2 fm is not satisfied, if it is greater than 2 fm, then this will be oversampling. If this is equal to 2 fm, this is perfect sampling. But if it is less than 2 fm, then you see this information is lost. And when you lose this information, this effect is known as aliasing, and then you can avoid aliasing by considering this condition or using anti-aliasing filters. Okay, so this is the sampling Nyquist-Shannon theorem, which I explained that Fs should be greater than 2 FM for reconstruction. So you see that when this is Fs is greater than or equals to 2 into FM, then this is this signal can be reconstructed. You see there are 10 samples in this one cycle. One cycle is completing here. You see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples. Here in this case, in one cycle there are 5 samples, and then here in one cycle there are 2 samples. So this is good. But here if you see when Fs is less than 2 FM, you see the number of cycles are number of samples are very less in one cycle. So here information is losing. Okay. So I have a signal A is equals to sine of omega m of t. We have to check for, and then amplitude is equals to 1, and then FM is equals to 1. So we have to check for 50 into FM, because you know Fs should be greater than or equals to 2 into FM. So 50 FM is good. 10 FM is also good, but this will not be good because the number of samples will be very, very less for the reconstruction. Okay, here the number of samples are enough for the reconstruction. So first, I will define the frequency of my signal, then sampling frequency, then time scale, then amplitude, and then I write my signal, then plotting, plotting the signal. So this is the first point, this is the second point, and then this is the amplitude from minus to plus. Okay, so see for Fs is equal to 50, I got, so it's here, I defined it here, 50 into FM. So I got 50 samples per cycle. So one cycle is completing here, so there are 50 samples. So when this will be 10 FM, so it will be here 10. So for the 10 FM, so there will be number of samples will be 10, and then for 0.5 the number of samples will only be 3, because is greater than or equals to 2 into FM is not fulfilled. So there are only 3 samples. This signal cannot be reconstructed. So that's it for your review. So I have made this file, which is the revision, and then this file has all the examples from for all your labs, starting from lab number 1, lab 2, lab number 3, lab number 4, lab number 5, lab number 6, lab number 7, and lab number 8. So this file I will upload to the Moodle. You will have it in your lab exam also. You can use this. You can use this file to solve your exam, because the exam will be open book. And then you are not allowed to bring any other thing, any other notes with you, because I already given all the data from all the labs. So you will have this file with you, and then you will be able to solve your exam. Okay, so that's it about the revision. And then I will upload this revision on I will upload a revision of video today, and also I will upload this example, so you can take reference and then you can study accordingly. Okay, so on Monday there will be 2 sections, section number 1 and 3, and on Wednesday section number 2. So please be prepared well for the exam, and I will divide you in 2 groups, and I will upload the PDF of the groups according to their timing. So please check your exam time and then come to the campus according to your exam time. Okay. Thank you.